Now what we want to do is, given a surface such as the one defined by f, I want to find all lines on that surface. And the way I'm going to do it is to use our parameter space, the Grassmannians from last week. I just created a polynomial ring in 4 variables with names y1, y12, etc. And what I'm trying to do here is to deal with an affine chart of the Grassmannian. Remember, these affine charts on the Grassmannian were isomorphic to A4s, to affine 4 spaces. And the way we related these 4 coordinates to lines was via the following matrix. So this matrix has row 1, 0, etc. and 0, 1, y21, y22. Remember, this was one of the charts where the first 2 by 2 minor of corresponding lines did not vanish. Then you could put it into these unique form. And now let's parametrize lines of this form while keeping yij's to be variables. I'm just going to go back up here, take my coordinate ring, but I want to change my base ring to be over A. So this is now coordinate ring of a P1 over A4, if you like. So over the affine 4 space times P1. I mean, now if you want to think of it in another way, to the polynomial ring A, I'm adjoining 2 variables uv. I'm going to construct the same matrix uv, and now I would like to multiply m with uv. This will then give me the parametrization of the lines. Let's do this by taking that part over here. So remember, uv times change of ring, but now of m to u. So if I were to try to multiply uv with m, this would throw an error. So I change m to be a matrix over the ring u. I multiply and then read the entries with lsec, element to sequence. Should take everything. Okay, so as expected, I see uv times m, of course, has first entry u, that's this one. Second entry will be v, and then this linear combination. Of course, I could have just written this manually, but it relates to the first expression, first construction that we have done. And now the next step is exactly the same. I want to plug this in to my f and then read the coefficients of the polynomial in uv. I just assigned this sequence of elements into ll, and I'm going to evaluate f on ll. Let's just see what this is. Okay, you see this is a polynomial in u and v. But maybe if I were to read its coefficients, it would be more fruitful. So let's do that. Okay, so now this is a sequence of coefficients. For example, where is this coefficient coming from? It's the coefficient over here of u cubed. And the final coefficient will be the coefficient of v cubed. Now what these 4 polynomials define is the common locus, common zero locus, would define something inside the affine 4 space corresponding to this polynomial ring A. And of course, every point on the zero locus, in the common zero locus, will annihilate this polynomial obtained by pulling back f to our line P1, which means the corresponding line is exactly in the zero locus of the surface defined by f. So let's first define the ideal defined by these 4 coefficients. There are 4 coefficients because f is of degree 3. If f was of degree 37, then there would be 38 coefficients. But in any case, I can define the ideal corresponding to these entries over here. And now I can define the scheme in the spectrum of A, so this is A4, defined by the common vanishing of these polynomial equations. Of course, I didn't define this. All right, so now what is x? This we don't know yet. For example, is it really 0-dimensional? Every point in x should correspond to a line. So if x is 0-dimensional, then there will be finitely many lines, at least in this affine chart of the Grassmannian. Okay, so here's what we learn about x. The dimension is 0, the degree of x is 27, and there are no rational points in x. So if you know that a smooth cubic always has exactly 27 lines, and this 27 is not very surprising, given that my cubic f was completely random, so you would not have expected it to have strange lines that do not line on an affine chart. So an affine chart covers almost everything in a Grassmannian, so to have lines that do not lie in this affine chart is a surprising event, and a random cubic will not satisfy the surprising event. So 27 makes sense. It's also maybe not that surprising that there are these 27 lines are not defined over Q. I'm also copying this points over splitting field command from upstairs. Let's see what this gives us. And this is why you don't want to use points over splitting field. So it took a few seconds to compute it, and the answer is here. So these are defining first the algebraic extensions of Q that you need to do. I think there will not be enough space. Right. So it was busy trying to define variables and the polynomials that these variables should satisfy so that they represent algebraic numbers, and then it would have extra equations. Anyway, this printout didn't even fit into my screen. And the command degree was essentially instantaneous. So this is why you don't want to find points over splitting field unless you really have to. Before we leave this example, let's turn this into a function because I want to use it again later. So I write function lines on first, let's say strata. It should take f as an input, and it will return the number of lines and perhaps additional data. I'm just going to copy paste this over there. Okay, finding lines on the surface, maybe I keep this command. What I don't want to do is to have any unnecessary information. Okay, so far so good. Let's go upstairs and copy paste. Okay, so what this function is supposed to do is that it takes a polynomial f. It doesn't do any checks. So if you give me the wrong kind of f, things will break. But anyway, without performing any checks, it creates this affine generic strata of the Grassmannian. It just creates the line, pulls back f via the generic line, computes the corresponding scheme, and then outputs the degree, dimension, and points. One thing about Magma is that if you just ask for the first output of a function, it will not evaluate these other things, which might be costly in terms of time. Therefore, you can add extra data here, even if it is expensive. Unless asked for, it will not take any time. Okay, so let's just check lines on first strata f. Okay, it works. And here's what I mean. If I say num lines equals lines on first strata, then num lines is only 27. I did not ask for the second and third outputs of this function, and therefore they will not be evaluated, saving some time. One thing we forgot about is to check whether or not the zero locus defined by x is actually reduced or not. We didn't have to check because I sort of knew f is supposed to have 27 lines, and when I got the right answer, I didn't worry. But in principle, you could worry, although there is a general statement in this case that what we are doing will not produce non-reduced loci. So let's now try this again. Okay, we also get this fourth output saying that x is indeed reduced, so we really do have 27 distinct lines. So far, I've been operating only on the generic affine chart of a Grassmannian, and this means that if there were lines inside of the complement of this affine chart, then I would be missing them. And let me give you an example of a surface that has this property. So f, again, is a cubic, and I construct the surface S, just checking that the dimension, degree, and the fact that it's non-singular is true. Okay, so it's indeed a surface, it has degree 3, it's non-singular. And now if we were to count the number of lines inside of f, we will get something less than 27. We already have our function, so I can ask for lines on first strata. It says there are 16 lines. The dimension of x is 0, so as expected. There is in fact a rational point. So when yij's are all 0, I get an obvious line, and this obvious line ends up living inside of f. Also, the scheme is non-reduced, so the degree 16 is correct. It really says that there are 16 lines living inside of this affine chart of the Grassmannian, so 16 points on this affine chart. But all smooth cubic surfaces have 27 lines. This is a classical result. So the remaining 9 lines lie somewhere else. Okay, let's do another computation. This time let's find lines on another strata. I'm just going to copy paste this paragraph Now I'm going to operate on another chart. What I did previously was that the minor corresponding to 1, 2 was non-zero. So it was that this first 2 by 2 matrix in this 2 by 4 matrix M was non-zero. So I inverted it, making it 1, 0, 0, 1. So this was the discussion from last week. But now I want this first 2 by 2 matrix to be 0, to have a 0 determinant. And then I will be outside of my affine chart. So once that's true, I can at least, let's put stars here for now. I can make it so that the second line and the first two entries in the second line are linearly dependent on the first two entries of the first line. That's what linear dependence means. The determinant of this 2 by 2 matrix vanishes. Therefore, I can get this a generic element, any element in this chart that I have in mind to be of this form. Moreover, I want to say, and this is not an affine chart, so I want to make it affine by saying M13 is not 0. So that would be the minor corresponding to the first row and the third row. So this gives me a 2 by 2 matrix by using the first and the third columns. And then the determinant of this being non-zero, I can always invert it. And therefore I can put this matrix in the following form. So what I did is that there was this unknown entry. So in trying to describe all lines satisfying the M12 equals 0, M13 not 0 condition, is that there is this undefined entry. So this is a variable. I can write Y11 here. And then the first and third columns were inverted to be brought into the identity. And then the remaining two entries are also free. I don't have an A4, but an A3, an affine 3 space. And I did not use this. So, okay. Now let's change this 4 to 3. So my lines satisfying these two conditions will all be representable by this 2 by 4 matrix with these three variables being indeterminate. And then the rest is the same. I form this P1 over A3 if you want. And then I parameterize my lines using this UV coordinates. And then I pull back F to this P1 corresponding to the U. And then I form the scheme X in the spec of A. So everything else remains the same. My F is the F defined over here. So this was the special one with 16 lines on the affine chart. Let's see what it does here. Let's look at the degree of X. There are 10 lines here. And let's just check that the dimension of X is 0. And also, okay, so X is reduced. It has dimension 0, has degree 10. Are there any points? Okay, and no rational points. It makes sense to create another function. Let's call it lines on second strata. Again, it takes F. And everything else, I will copy this paragraph. And now I want to return the dimension, degree, etc. of X. I will just borrow this from the function above. Okay, so it will tell me the degree, dimension, rational points, and whether or not X is reduced. Let's check lines on second strata. Okay, that sounds about right. Now, as an exercise at this point, you should look for the other strata. I wrote down the generic strata, the open affine set of dimension 4. In its complement, I did not take its full complement. Its complement will be the lines where the first 1, 2 matrix minor is 0. But then within this subset, I said, well, take the condition where the minor 1, 3 is not 0. Therefore, this is not everything. It is possible that the minor 1, 3 is also 0. And then you could look at minor 1, 4, etc. And there are 6 such strata. And if you have these 6 parameterizations, 6 subsets of the Grassmannian, and search for lines inside of each of these 6 strata, then you can find all lines in a given surface. And that's an exercise would be to write a function that finds all lines. Now you can do as I've done. For each strata, you can write down a function. So by the way, finding all lines, maybe count all lines is simpler. And then you can either do as I've done and write down 6 functions, or you can be a little bit more clever about how you can construct these things on the fly and then construct the scheme sort of more uniformly. Since all this expression here was uniform, I don't want to repeat it again and again, so you can try to cook up a more elegant way to go through these 6 strata. Again, that will be a coding challenge if you want to make it more elegant.